Hey there. So let's start talking about Chapter 8. So Chapter 8 is interesting because it starts getting us into bonding and how all that ties together and works. So let me erase this. So quick review, there are three types of bonds. There's the covalent and there's the ionic. Remember that those two are essentially the same, just the ionic are the super strong ones. Or better said, the covalent ones are just really weak ionic bonds. That's a simpler way to describe it. And so there's covalent, polar, nonpolar, and then there's the metallic bonding. So first, remember that if we're doing ionic bonds, bonding is results in the lowering of all energy because atoms want to be in a more comfortable position, and if they didn't do that, then they wouldn't bond together. So now that we've talked about that, let's talk about metallic bonding. Just a bit. We won't go into a deep dive. But the reason metallic bonding is different is because instead of actually bonding, like like let's say we have hydrogen and fluorine, the way these two bond is they share electrons. Like I have electrons, let's share. And so they grab each other in the polar way. Like it's the opposites attracts, and so this one being a positive ion is willing to donate its electrons to the one that wants the electrons. Uh, so everyone's okay. So you're electron deficient, or you want the electrons and you're willing to give the electron. It works out. Metallic bonding isn't about sharing, it's about assimilation. Like you can say that the metallic bonds aren't actually bonds, it's just like you're now part of the whole. The way this works is because they're more communist actually. So when you have metal atoms, like let's just say these are tungsten just for kicks. I don't know if tungsten actually works like this. And they have like three or four valence electrons. When you put the tungstens together, like the electrons just get shared by all of them and they just kind of float around. Like only the valence electrons, mind you, but the electrons just kind of like hang out and they don't have any issues. This is actually what gives metals like bigger like quantities of them. Uh, their flexibility and ductility is because this is like a bond. Like you can't bend it, you can't shape it, you can't do anything with it. But metals like don't really care. All they have to do is have contact with each other. And then the electrons just kind of float around like hobos. And that's why electricity works too, because you can push electrons in and then electrons come out. But that's what metallic bonding is, which means that it's not actually that complex on the general level. Like what we're talking about, we're not going to get anything any deeper or more complex. So the majority of what we talk about are ionic and covalent bonds, because they're actually the interesting ones. So, two things. The most stable state for an atom is to have eight electrons, eight valence electrons, I mean. So if I have like tungsten, I just like tungsten a lot. Actually, no, that's a metal. That won't work. I mean, it would, but it wouldn't make sense. Let's go with like selenium. I don't know how many selenium has, but let's say it has like five or four. Yeah, five. Five is best. Selenium wants to have eight, like naturally. Like when it's by itself, everything's fine. It's not gonna like do anything or explode. Uh, but when placed in a reaction, like enough energy to get it started, it's gonna be like, guys, I need more electrons. I'm not happy. And so what it will do is it will find an element, let's just say oxygen, who has three electrons, and then they share, or at least has three electrons to share. Um, and so what you end up with is going to be a compound where all of a sudden I now have my three electrons that I've been missing. Oh my gosh, now I'm happy. And that's the basis of how it works. Lewis structures are actually how we illustrate this. And pretty soon, if I don't haven't skipped anything, we'll jump into doing structures. So, very important to note is that the formation of ionic compounds is exothermic because it is a lowering in the amount of energy that is in the system and what you have. So like if I have sodium and I have chlorine, these two have their own levels of energy. I put them together and it releases heat because they are lowering in energy. So the heat has to go somewhere and it comes out, and that's why we feel it as heat. So when something is like hot in like the general sense and it's radiating heat, that actually means it's lowering in temperature, not that it's just hot. It's actually lowering in temperature. And when something is cold, its temperature is going up because it's drawing in heat from the surroundings. Now that we know that, yep, covalent bonds is based on the sharing of electron pairs, and the driving force behind any bond formation is the lowering of overall energy because they want to be in a stable position. Um, the electrons in a covalent bond are not always shared equally. Uh, that's when you get into exceptions, which usually come from boron and the noble gases, because they can hold more or less. Nonpolar covalent bonds result from equal or nearly equal sharing of electrons, and polar comes from unequal sharing, which makes sense. Because when one side pulls the electrons toward itself, it's really making like that side of it more negative. That's not to say that they aren't sharing and that they don't have their octets, but it is a little like that. Like imagine you're in a tug of war. If you both have the same amount of strength, like this, you're not going anywhere. But let's say I'm just jacked, and the person I'm going against hasn't gone to the gym for a while. I pull harder, and so I'm leaning more this way while they're pulled a bit towards me. I haven't necessarily won in that sense, but all the force is on my side. All the rope is on my side. And that's how the polar non-polar thing works. I am more electronegative than that person, so I pull the electrons towards me. And that's how an atom works. And we talked about that in a previous video. So remember Falkland? FOClN, the most electronegative elements. These are important. Uh, and the threshold. So remember when I went over the spectrum of covalent to ionic compounds? So remember this was non-polar, this was polar, and this was ionic. So the threshold at which it crosses over is if the difference in electronegativity between the two is 0 to 0.4, 0 to 0.4, then it's going to be nonpolar. If the difference is uh, from that to 1.9, then it's going to be polar, and anything above that is going to be ionic. Reason being that nonpolar, like if you have two of the same element, it's going to be like an even match in the tug of war. So if I'm fluorine and he's fluorine, we both go to the gym at the same time. Like neither of us is stronger than the other, so we don't really like lean one way or the other. Same if you like put fluorine and oxygen together, like they're so close that there's going to be like a very slight pull on one side, but they're still almost equal. So no one's going to win. Um, so yeah, so kind of just to illustrate it, kind of what's on the slides, when you have atom here, and you have a covalent bond, like nonpolar, it's going to look like that. And then when you have, uh, it says, yeah, polar covalent, I meant to make those dots. Atom, it's like the electron field, all of this is going to be negative, and like this size it can vary. And then when it's ionic, it's just going to be completely separate. So all of that right there. And then you get like a tiny little positive, whatever. You kind of see how it's like splitting up. Like I start squeezing it and then I bring it over here and then they're separate. Uh, that's kind of what happens. So polar important properties is solubility and melting and boiling points. That goes into intermolecular forces. Maybe not the solubility, But it does explain why like oil and water don't mix. So for example, oil is nonpolar, so it has atoms that versus oil and water is ionic intrinsically, if I'm not wrong. Yeah, so water is polar or ionic, and so it's gonna be like this, and these two don't really get along. But if I had another polar something like that, it would dissolve, like these two would dissolve each other, whichever one wants to make the other one aqueous. This is why oil and water don't mix, because polar versus non-polar. And yeah, but the melting and boiling points goes into IMFs, which we'll talk about later, which are not bonds between atoms, but how molecules bond to each other. Molecules of the same substance. So the simple approach, like we mentioned, is ionic compounds are metals and nonmetals, but like it's more the electronegativity on the spectrum. Uh, Electronegativity difference doesn't take into account the oxidation number, uh, which means that you can't do it between ions. Like if I'm given H plus and something else, like maybe O minus, things are a bit different. Like if you remember, O minus is going to have a much lower electronegativity because it's a lot easier to get rid of that electron. Like you have to put in less energy to make it fly away. Like, that's just what it is. So lower melting points usually mean covalent bonding because you can put them, you don't have to add in as much energy for it to split apart. The bond isn't as strong. So bond energy is the energy released when isolated atoms form a covalent bond. Remember when I said it was the lowering of energy? So what happens is when I have an atom here, they're currently in like this really funny state where they have energy. The electrons are like, yeah, I got this, guys. Uh, and to get them into a reaction, you add even more heat to get them to do stuff. And then the second in which a bond is formed, they come together, and neither one needs as much energy because they're sharing their electrons. So all that energy gets radiated out, including the energy that the electrons were holding, because now they're sharing. And that's why it's exothermic. And the reason covalents have, yeah, ionics demonstrate this more, where you have to put in more energy to get them to do anything. So, vice versa, covalent bonds, since they're so weak, I'm just going to draw like that, you barely have to put any energy in, which means that if you say, I don't know, had like oxygen inside O2, for example, if you had O2 in a pot, like you don't even have to have it at room temperature for it to start boiling and evaporate because it needs so little energy for those covalent bonds to start uh, doing stuff. That's not a very good analogy because O2 isn't a bond, but the idea remains really low boiling point because electronegativity. So bond length is the distance between the nuclei and of the bonding atoms where the potential energy is at a minimum. I don't actually understand this. I forgot about this. Bond energy. I should write that down. Study bond energy. Mm-hmm. Yeah. So once a bond is formed, same amount of energy is needed to break the bond apart. Uh, Law of conservation, I guess. But the bond length is distance between the nuclei of the bonding atoms where potential energy is at a minimum because they want to have the least amount of energy. So it's like finding that sweet spot where we have the least amount possible. So it doesn't actually explain how to do anything with that, but okay. Double and triple bonds. So now we're starting to get into Lewis structures. So I can explain this. The way Lewis structures work is that we draw our elements as letters, or the symbol on the periodic table. So, for example, carbon, calcium is better. And then we draw the electrons around them. So calcium has lithium, beryllium, boron, carbon, everywhere, nitrogen all through the year, and oxygen. Calcium is pretty far down. So calcium has two valence electrons. We only care about the valence electrons because those are the ones that are involved in bonding, and Lewis structures are representations of bonding. So calcium gets 2 valence electrons. And if I had another element, I don't know, like oxygen, which has 6, oxygen would be like 1, 2, 3, 4, 5, 6. They come in bonding pairs, by the way. So the electrons come in pairs. So after that, what we end up with is how do we put these together? So let's say I want calcium oxide. So I know based on previous units that calcium is is a +2. Yeah, so 2 plus, and oxygen is a 2 minus. So if I want calcium oxide, it's just going to be CaO, simple as that. Um, Now what we do is, to draw a Lewis structure, we draw lines to represent bonds between them. So when these two want to make a bond, what they're going to do is they're going to be sharing their atoms. So calcium is going to have a sharing of electrons with oxygen. This bond represents the shares. So let's say oxygen has an electron and calcium has an electron. What they're going to do is those electrons are going to get put together to form a bond. So now each of them technically has a pair. It could look like this as well, where boom, 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 and then they connect like that, and there's only 2 electrons that they both have. So it's like these 2 electrons count for both of them at once. Now you can add in more bonds. Like if I have calcium, I can do 1 and 2 to oxygen, and that is 1, 2, 3, 4 electrons that they're sharing now. Now the idea with Lewis structures is to arrange the atoms or the elements using your the total amount of valence electrons. So I have a total amount of valence electrons determined by what elements are involved and how much of them. And you're going to put them and arrange them so that all the elements have 8 electrons surrounding them. So let's do it for calcium oxide. I'm pretty sure this is a valid element, or a valid compound. But we're going to do it like this. So Ca and O. The first step in drawing a Lewis structure is to put in the least electronegative element, or the one that is closest to the bottom and to the left of your periodic table. That's just the one that goes in the center. So now we count how many valence electrons that we have to use, like how many we have in our bank. So calcium has 2, oxygen has 6, so we have 8 valence electrons. 8 valence electrons. After that, I'm just going to double check the steps just so I mean, this is review, so I don't feel bad. Alright, step 2, draw the skeletal structure, which is essentially, these have to be connected, so boom, we put one in. And that's -2. -2. After that, we fill in the lone pairs on the outer ones. So calcium is the less electronegative element, so oxygen gets its lone pairs first. So 1, 2, 3, 4, 5, 6. And yeah. So we ended up with that, where calcium only has no valence electrons. And that gets into our fourth step. Like, we've placed the remaining electrons on the central atom, any we have left, and if it doesn't have an octet, which it doesn't, it only has 2, then what we have to do is we have to move our electrons into sharing. So these 2 get erased. How many does calcium have now? 4. Erase these 2. 2. So now it has 6. So to get the 8, we draw the 4. Huh. I didn't realize that this compound did this. It's probably one of those exceptions. These aren't very common to have 4. Calcium oxide. Let's see what Google has to say. Calcium oxide. Calcium oxide Lewis structure. Oh, that's interesting. Wait, no, this is carbon oxide. Carbon dioxide, what? I want calcium oxide. That's what ChatGPT has to say. Uh, the Lewis. Yeah, but those are the steps, and that's how it works. So here we go. ChatGPT is going through it. Um, Ca plus O, because the bond is ionic, not covalent. What? Wait, so ionic don't have Lewis structures? ChatGPT is telling me that Lewis structures are for covalent compounds. Okay. So what do we draw for ionic compounds? Oh, that makes sense. Okay, I just had something change. So this technically doesn't work because it's an ionic compound. It's not covalent. And it goes back to what I was saying, kind of reading off the slides, with this is what an ionic compound looks like, while this is what a covalent compound looks like. Notice that they're sharing the electrons, but in this one, it's entirely separate. So, ionic compounds, we write the ions. We say that we have calcium, which has lost two electrons, so 2 plus oxygen, which is 2 minus because it has drawn all the electrons over to itself. That's actually really interesting, and I didn't know that. So Lewis structure makes more sense in other contexts. So this doesn't work because they're not sharing. Oxygen has taken all of the electrons. Let's switch over to hydrogen, hydrogen dioxide. Wait, no, dihydrogen monoxide? Yeah, H2O. Okay, H2O. So we have H2 and O. So you would think that the least electronegative would be hydrogen, but hydrogen is weird. So in this case, we're just going to choose oxygen as our least electronegative. And then, following the steps, we draw the skeletal structure, which is we have oxygen that has to be connected to 2 hydrogens. And then we count our valence electrons. So oxygen has 6, hydrogen have 2. So that's a total of 8 in our bank. After that, what we do is we subtract for the skeletal bonds. So minus 4 equals 4. Now, hydrogen is an exception in the fact that it only has one subshell, so it doesn't need to have an octet. It's the exception. It only needs to have 2 valence electrons. So this is fine and this is fine. But currently, we still have 4 valence electrons left over to use. What do we do with them? Well, we just put them on our oxygen. And boom, and then that is our Lewis structure. No problems. Let's now do carbon dioxide. Carbon dioxide is another good example. So CO2. Carbon is the least electronegative. Oxygen and oxygen. So we count the valence electrons. So carbon has 4 and oxygen has 6. So that's 6 plus 6 is 12. And carbon is 16. 16. And minus 4 is 12. And then we do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, completing the octet. And let's see how many we have left. So 6 plus 6 is 12. Minus 12 is 0, which means that we don't have any electrons on the center. This is going to be important later, like how many lone pairs there are on the middle atom, so you can know what the shape of the molecule is. This one, in fact, is linear, so it should look like this, because it's straight. Because these electrons, so you know how opposites attract, positive and negative attract each other? Problem is, negative and negative repel. So what these two ends are going to want to do is get as far away from each other as possible, which means they're going to have 180-degree angle in between them. And it gets more complex when you have more of them. So, moving on, I think we're going to get into some more exception now. Remember, it has to be a covalent compound. Exceptions include stuff that involves sulfur, and like fluorine and boron. So theirs are incomplete octets, which are instances in which you run out of electrons before you finish, and others are, what are they? I forgot. Oh yeah, when you have too many on your central atom. So that's an expanded octet. For example, SF6 is going to look like this. S1, 2, 3, 4, 5, 6, and then all of these are going to have an F on them. That means that sulfur actually has 12 electrons on it, which is not the octet rule, but we just let it slide because it just happens that way. When you draw the structure, it's actually kind of intuitive because you don't count the electrons and then draw the bonds. What you do is you draw the skeletal structure first, and then you subtract from the total valence electrons, and you're like, oh my gosh, that's so weird. Sulfur has 1,000,000 valence electrons. So the other version of it is the incomplete octet, like boron, BF3. So boron with three fluorines is going to be actually like fine. 1, 2, 3, 4, 5, 6. 1, 2. And everything's going to be okay. But boron does not satisfy the octet rule, but it's used all its valence electrons, so there's no problem. So you can also use this to figure out. Hold on. Quick note. There's something called a resonance structure before we get into determining ions. But the bonding in some molecules is not described by a singular structure because there's ambiguity. For example, O3. O3. This compound has oxygen in the middle, plus an oxygen and an oxygen. And we have 18 valence electrons. We already have 4 that are used, so minus 4, so we have 14. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So minus 12. And that's going to leave us with 2 valence electrons. And what do we do with those? Well, the oxygen in the middle is missing some, so we just put them on there. There's a problem, though. Oxygen cannot be an exception to the octet rule. And it's missing 2 of its electrons. So we already know what to do. What we do is we put another bond where it shares with the other, with another one of its molecules, or atoms. Problem is, which one? It can do either side. It can be on this side or it can be on that side. You can choose either one. You can take it from here and put it over there. Or, oh, that didn't erase. You can take it from here and you can put it over there. And everybody's happy. However, those two versions are not the same. Now in properties, they're exactly the same. No one's going to have a problem with it. But the truth is, this substance has what are called resonance structures, where the state of existence of O3 is that an atom where it has the 2 electrons that are making this right here are actually jumping back and forth because they don't know which one to decide on. Because both work, so they just go back and forth. I don't actually know what that does to things, but they just do that. But that's called a resonance structure. So every variant, or every possible variant of a single compound is called one of the resonance structures. So the total is how many variants you have. So this is 1, this is 2, so thus you have 2 resonance structures within this compound. And of course there are others that have more and others that have less. Actually, you can't have less than 2, so that's okay. Now let's talk about ionic compounds. So a really easy way to know what the charge is on an ionic compound, or an ion, specifically anions, is to actually draw your Lewis structure. So a good anion is NH3. That's actually a cation. NH3, if I'm not wrong, has a charge of plus, and this is ammonia. Um, so what we do is we draw the Lewis structure. N, and then 3H. So now we count how many we have. I don't know where nitrogen is. Nitrogen has 5 valence electrons, plus 3 from the hydrogen is 8. 8 valence electrons. Yes. Minus 6 for the bonds we have. That's going to give us 2, and we put it there. Something's wrong. I'm not confused. How many valence electrons do you have? 5? Oh, I'm going to pause this.